IonQ works with Pacific Northwest National Laboratory to build a new quantum computing supply chain. This photomicrograph shows a chain of barium ions in an IonQ quantum computing system. The width of the chain is only slightly bigger than the width of a human hair. Dare we say it? Pacific Northwest National Laboratory has teamed up with IonQ to come up with a method for producing barium ions for quantum computing that could lead to, yes, that's right, a quantum leap. The public-private partnership could open up a new avenue for developing more resilient, more powerful hardware for trapped ion quantum computer. The key technology involves using barium ions as the foundation for qubits, the quantum equivalent of binary bits in classical computing. IonQ's work with PNNL to secure the domestic supply chain of IonQ's quantum computing qubits is a fundamental step in the mass commercialization of quantum computing, IonQ's president and CEO, Peter Chapman, said today in a news release. Qubits are at the core of our quantum computers, and this collaboration with PNNL lays the foundation for us to scale manufacturing of our system. The partners say PNNL's production process will provide a steady supply of barium-based qubits, using a microscopic smidgen of source material. That should make it possible for IonQ to reduce the size of core system components, which should in turn make it easier to network quantum computer. Quantum computing relies on seemingly weird effects on the microscopic scale, in which a qubit can represent multiple values at the same time rather than the rigid 1 or 0 values held by binary bit. Researchers can use either superconducting circuits or supercooled, laser-trapped ions to create qubit. In the past, IonQ has relied on industry-standard ytterbium ions, but in December, the company announced that it's switching to barium ions for its next-generation hardware. According to IonQ, barium qubits are preferable because they can be manipulated by laser light at wavelengths that are less damaging to components than the ultraviolet light required for a ytterbium qubit. The technology also opens the way for faster, more accurate quantum computation. By leveraging the inherent advantages of barium qubits, we are now able to access new features for building advanced quantum computers that will be relevant for solving critical societal problems, Young-Sam Kim, IonQ's co-founder and chief technology officer, said in December. Computer scientists say quantum systems are particularly well suited for solving optimization problems and for developing new materials for industrial and pharmaceutical application. For years, PNNL's researchers have been working with IonQ and other players in the quantum computing field, including Microsoft and the University of Washington, through a consortium known as the Northwest Quantum Nexus. We are thrilled to contribute PNNL's chemistry expertise to the quantum computing community, said Marvin Warner, a materials scientist at the National Laboratory. It is particularly satisfying to collaborate on what will become the core components of IonQ's system. Although IonQ's headquarters are in Maryland, the venture has multiple connections to the Pacific Northwest. IonQ is a platform provider for Microsoft's Azure Quantum as well as Amazon's Breakit Quantum Cloud computing service. Before taking on the CEO role at IonQ, Chapman spent several years as director of engineering for Amazon Prime. The company already has a significant presence in Seattle, and it's getting ready to select a location for its Seattle-based product engineering facility.